Hello there, welcome to a presentation on the absolute value of a real number x. Recall that in our previous presentation on real numbers, we went as far as introducing the concept of an absolute value of a real number x, and we defined it as follows. We said the absolute value of a real number x is x if x is greater or equal to 0, or is minus x if x is strictly less than 0. So that simply means that if we've got a value, a numerical value like minus 3, and once it's absolute value, we simply need to apply this definition carefully. First of all, we've got to look at what is in the absolute, in the brackets there, as the bars, whether it's greater or equal to 0 or is less than 0. But most importantly, what we discussed before is that the absolute value of x is always going to be a quantity which is greater or equals to 0, and equal to 0 when you say absolute value of x is equal to 0, that would mean that x itself is equals to 0. That is very important. So then now here x is not our x is minus 3 is not equal to 0. Then we have got to check whether it's greater than 0 or less than 0. Now if it's less than 0, to achieve that the answer to this is greater or equal to 0, we simply need to put a negative sign before the x we're given as minus 3, which means we're simply applying the rules of combination of signs, and then this will give us 3, which is greater than 0. So in the case we've got 4, absolute value of 4, we notice that 4 is greater than 0, or we can say 4 is greater or equal to 0. It doesn't present any contradiction. Then in this case the absolute value will be equals to 4. And what is important, which I want to talk about now, is what do you do if you are given something like 2x plus 1 as an inequality, and you are told that this is less than, let's say, 4. Or on the other hand, you get something like 3x minus 1 greater than 4. So this is what we call inequalities involving absolute value. So first of all, let's start small, this one, and let's say we're simply talking about the absolute value of x less than, let's say, 2. Now if we talk of absolute value of x equals to 2, we know from what we've seen that in this case we'll be talking about 2 exactly there and minus 2. Now but then we're saying 2 and minus 2 are at a distance 2 from the reference point here, which is 0. So if we talk of less, we'll be talking like numbers like 0, like 1, minus 1, and any number in between there. So this actually gives us an interval which is from minus 2 to 2. That's what this gives us. So on the other hand, if we consider the opposite inequality of saying x, absolute value of x greater than 2, which means again we've got our 2 as a reference there, absolute value equals 2 as a reference. So if we say greater, the numbers which are greater than 2 are on the right of 2. Then we'll be talking about numbers which are in this region. But those are not the only numbers which are at a distance greater than 2 from 0. So we know that minus 2 is a distance 2, so then minus 3 will be at a distance greater than 2. So again, we're talking about numbers in that region there. That's what we should understand. So what we have here, basically, this gives us to a situation which is equivalent to saying the x's we're talking about here, they're less than minus 2, or we're talking about x's which are greater than 2. And then this basically what we have here you notice that we've got two sets here. In this case, we've got a set of real numbers such that x is less than minus 2. That's a set using what we call set builder notation that represents this. Then O, this O is going to be represented by a union. So the x's we're talking about here is union of two sets, this set and set of real numbers again, such that x is greater than 2. So you should understand that when you get this kind of situation, we have this kind of a set using set builder notation. But on the other hand, in this situation, you can do exactly something similar and say here we've got two sets, which one of the sets we can read from here up to there, whereby we're saying we're talking about the real numbers x such that x is greater than minus 2. But if we start from here to there, we'll be talking about real numbers x such that x is less than 2. So in this case, what we have here, you've got numbers greater than minus 2 going this way, and on the other hand here we've got numbers less than minus 2 going that way, which means now this set we're talking about, which satisfy this condition, we're talking about what is common between these two sets here. We can take this as set A and then this as set B. Then what is here is what is common, which we call the intersection. So we'll say now this is simply the intersection of these two sets, but this gives us what we call an open interval, which we can represent this way with an open bracket like that, and then 2, that's what we have there. But in this case here, this is still an interval, this set is still an interval. Equivalently, we can simply represent it as interval from minus infinity to minus 2. Union, in this case the interval from 2 to plus infinity. It's very important to understand these notations and what they mean like that. So if we were the opposite case, like for example with x, absolute value of x less or equal to 2, then this will be equivalent to what we call a closed interval, which would in this case represent by this kind of a notation, say minus 2 to 2 inclusive, without including minus 2 and 2, but here they are not included. And then if we're to represent this on a number line, then we would simply do the following. For these two, we'll just draw a line here, put a shaded dot there, and then for minus 2 again we do the same, and then join the two to indicate that the numbers we're talking about here are numbers which lie between the two numbers there. But in the case of the strict inequality like this one, which we have here, then we'll do this, we'll represent them differently in terms of the dots here, because 2 here is not included. Then this is what we'll do. For this part, which is greater than 2, we'll simply draw an open kind of a circle there and put a dot, then have an arrow pointing that way to indicate which numbers we're talking about. And for this one, we'll draw a line again and point it that way. That's what we'll do to that. So then this would be called a closed interval. So I hope you understand now that these arrows here represent this inequality. For this one, would have absolute value of x less than 2. That will equivalently give us an interval this way, which is minus 2 to 2, which would here call it an open interval. So the brackets here communicates something. When you have these round brackets, it means that 2 is not included. But when we got the square brackets here, meaning that 2 is included, making that a closed interval and this one an open interval. Now, let's now look at some problems involving inequalities which would solve in a similar way would solve equations. Let's say, for example, at 2x plus 1 greater than 3. So what we know here is that what is in brackets here can be either less than 0 or greater than 0. So in that case, what we would do, solving this kind of inequality, we would consider two cases. We would say now if, that's case number 1, if 2x plus 1 is greater or equal to 0, that would mean that 2x plus 1 is greater than 3. That's what that means then. Then solving this, let's say by adding minus 1 on both sides first here, we'll get 2x greater than 2. Now it's adding minus 1 here, we'll get 0 plus 2x, and then we get 2. Then this, what would take us to dividing both sides by 2, this will get us x greater than 1. And then the next case we'll say, or so case number 2, if 2x plus 1 is less than 0, then that will mean that 2x plus 1 is actually less than minus 3 because of this being greater than 3. Then solving this again, we would solve it by similarly by adding minus 1 on both sides of the inequality, getting 2x less than minus 4, and then getting x less than minus 2. Then that's what we have there. So we've got this inequality and that. So to represent the solution to this now graphically, what we do, we come to 1 here and draw again a circle, open there and show that this number sits in this direction. And in this case here, we'll come again and do that and have that. The open circle there just indicates that these boundaries minus 2 and 1 are not included. And then again, you must remember that you can represent this set solution. Let's say set solution here is, you can represent it as intervals. You can say now it's minus infinity to minus 2 union 1 to infinity, which is exactly the same thing as saying this is a set of real numbers such that x is less than minus 2 union set of real numbers such that x is greater than 1. And so the next example, I would like to do the one which involves the inequality in this way. Let's say 3x plus 1 less or equals to 5. So having talked about this one, which is strict inequality, I would like you to figure out how you deal with something like 2x minus 3, let's say 2x minus 3 greater or equals to 6. You must be able to do this as an example for yourself and do the kind of representation of the solution in all using all the variations I've looked at here in this example. Now let's look at this inequality. That's 3x plus 1 less or equals to 5. So in this equality, we need again to reflect on what we had here when we said the absolute value of x less or equals to 1. We said this was equivalent to simply saying that x lies between minus 1 and 1. So again here, we just look at what is in the brackets there as lying between minus 5 and 5. So we'll be saying 3 plus 1 lies between 5 and minus 5. I hope you see the difference here, that in that case there, here we're dealing with what we said we're dealing with a union, and here we're dealing with an intersection. Then we can actually work with this as one piece like that, instead of we're looking at two separate inequalities. So what we'd now do, would now want this inequality to govern x. In other words, we need to be left with x there less equal to some number there and the greater equal to some number here. Then what we do then, we just simply add -1 on the to the three terms which are in this equality. Then we get -6 less or equals to 3x, because here we're going to get 3x plus 0, and then in this here we get 5 minus 1, which is 4. And then simplifying this, we get dividing both sides by 3, we'll get this -2 less equal to x and 4 over 3. And then we've got that interval there, which we can represent simple as a closed interval from -2, 3 over 4, which is also equivalent to talking about a set of real numbers, let's say x real numbers, such that, so in this case here we're talking about real numbers x greater than -2 less or equal to 4 over 3. So in this case, you can see that to put it as a set Peter notation, you simply need to take this inequality and then write this set in this way. So represent that on the real number line, would have the following. Having a rough sketch here, you can just draw your rough sketch, have a reference point 0, because it's inclusive there. What would have here, get -2 here, would have a solid dot to indicate inclusivity, and then there we say it is less than 3, which is less than 1 and a third. So there we draw a line, and again we have that. Then the set of numbers we're talking about is in between here. Right. So now you can now see how we can draw this. We can solve these inequalities and represent their solutions. It's very important that you know the different notations, like as an interval, closed interval, as is closed interval, set Peter notation, and you represent that graphically. So the next thing is to look at this in terms of the graph. You remember absolute value of x is equals to x or minus x. X if x is greater or equals to 0, and this side if x is less than 0. So now if we now come to a system of coordinates like this, we can notice that if we take positive values, like if I say absolute value of 1, our place can say it's 1 on the x-axis, then we get the point there. For 2, get 2 again, point there. Then on the other hand, if it's negative, we have that for -1, -1 give us 1 there. Then if -2 will give us 2 there. Then in looking at this way, we can actually get to a point where we look at the absolute value, not it's just a definition, but as more of a function. At 0, we know that we have the absolute value of 0 being equal to 0, so we've got that. So what we notice here is that actually evaluating this function this way, we can now recall that we've got a function which is y equals to x, which is the bisector of the third and the first and the third quadrant, and we also got a function y is equal to minus x, and which is a bisector of the second and fourth quadrant, which is actually saying now, if we look at this as a function, this is a function which is a typical example of a function which is defined piecewise, because it has got one expression for the one part of its domain, and another expression for in this case, the negative numbers, a part of its domain. So that takes us to the following idea, that this absolute value is as closely related to these two types of function. Y is equals to x, and the y is equal to minus x. So this takes us to a idea that later we can look at looking at this situation for the absolute value. It means that for this function, we would ignore this part of the graph, and for this other one, this part of the graph is cut out, is not in the domain. Then we remain with something like this, which leads us to a graph which looks like this, which you can say this is a graph y is equal to f of x equals to the absolute value of x, which in this case we'll be talking about the absolute value function, which we're going to later look at the properties of the function. For example, the one which is obvious here, that this is a symmetric function around the y-axis. Then we'll maybe later look at other variations of this type of a function. Otherwise, at this point, I hope you've got the idea of how to manipulate inequalities involving absolute value and how to represent them graphically and represent them using set builder notation. At this point, I would like to say thank you for listening. My name is Charles Wasfani Msipa.